controversial. Anyway, so let us begin. Okay, so this talk will be an overview of the subject of earth sciences. We're kind of what is it, why you would want to study it, and then I'm going to go into quite some detail about what earth sciences are at Edinburgh. Okay, and then hopefully, if we've not run out of time, something about some of the teaching methods we use and whatnot, and why you'd want to come here. So here is a lecture theatre. Okay, you're all sitting in a lecture theatre. So this is kind of the experience you'll get when you're at university. There'll be some kind of old white guy at the front with a beard, like this. Some students paying attention. And that's not why I've shown you this picture. I've shown you this picture because everything in this room and everything in that room has ultimately come out of the ground. Okay, so it's come out of the ground. So you've got some plastic on the floor. They've got a nice plastic carpet here. Some metal on the benches. Some mercury up in the lights, maybe. Even the wood. Okay, so that's grown on trees. And the trees require kind of nutrients out of the ground to grow. So understanding kind of these processes of how we can get this stuff is an important aspect of earth sciences to kind of make our I guess, our society work. So that's one of the motivations for doing earth sciences and understanding the earth is how can we get those resources and how can we get those resources in a safe and sustainable way that doesn't damage the planet too much. So how do we do that? What do we do as earth sciences? Well, at the most fundamental level, what we do is we look at the earth and try and understand it. And back in the day, when kind of the subject was first kind of emerging in the 18th century, that was really looking. We were using our eyes to look at things around us, and we were doing things like making geological maps to understand the history and evolution of the planet. So this picture of the Earth up here, the top middle there, that's a geological map of the Earth. That's kind of one of the things that we will do as part of the geology degree. But it's much more broad than just looking with our eyes now. We use all kinds of different techniques. So earth sciences is really all about applying all of the physical sciences, so using chemistry, using biology, using physics, to look and understand and model how the Earth works. So, for example, this image down on the bottom left, your left, my right, is a false colour satellite image of the ocean colour. So actually, it's kind of colour-coded from blue to reds, but actually that's the greenness of the ocean. So one of the things we're able to do using remote sensing is monitor where in the ocean biological activity is happening, and then we use our understanding of physics and chemistry to try and understand why some regions of the ocean, say in the middle of the North Atlantic or the Southern Pacific or Northern Pacific, there's very little biological activity, whereas the physics and chemistry of the water in other regions allow for much more kind of activity to go on there. And that's important for understanding, life in the oceans, and it's quite nice that we understand that. But it's also important because we eat stuff from the ocean, so we need to figure out, how we can use that resource sustainably. But also that activity, that basically photosynthesis in the ocean, that's drawing down carbon dioxide from the atmosphere. So understanding the impact of changes of the physics and the chemistry, the supply of nutrients, the movement of water, how that can affect the potential for the ocean to sequester CO2 is a really important question in the earth sciences. We use techniques like using gravity surveying. So this is a map of the gravitational potential at the Earth's surface measured by satellites. And we also use the physical sciences not just to look and see what's there, but also to try and model and understand processes that happen deep within the Earth as well as the Earth's surface. So there's all kinds of different aspects. We want to understand how this fantastic thing that we live on kind of works. I should also point out that there is one image up here which is kind of the odd one out. Anyone hazard a guess to which one that is? So it's this one, top right. That's Venus. Okay, so we're not, it says earth sciences, but we're really not limited to the Earth at all. We're interested in all kind of planetary sciences as well. So if you have something against the Earth, then you can study another rocky planet. So also, one of the motivations for doing earth sciences is kind of the current kind of climate kind of crisis. So there were over 10,000 people out in the centre of Edinburgh yesterday protesting about our inaction on climate change, which is, I guess, good to see so many people care, but also bad that nothing is happening. But anyway, so the problem, and you might have seen figures like this kind of before, so these are from a report that came out, I think last year, showing what we would have to do to get this. So the graph on the left is the grey line going up and down. That's the actual average temperature of the Earth, kind of a lot of variability year to year, but you can see it's kind of this constantly increasing kind of trend here. And if that continues, okay, we'll get to 1.5 degrees Celsius warming above the pre-industrial values by around 2050. Okay, so that would be bad. Okay, it would be much worse if we carried on going up to here, and that will happen if we carry on doing what we're doing. So the plan, the super secret plan, no one knows what the super secret plan is, but there is one, is to stop the temperature warming and try and keep the global temperatures below 1.5 degrees C warming. So how do we do that? Right. So one of the so basically there have been the IPCC have done a bunch of different studies looking at what kind of different scenarios we could do in the future to bring down our atmospheric CO2 levels that would allow us to have temperatures like this. And this is an example of that. So this is us now. So we have to kind of stop burning fossil fuels to make electricity. So that's the grey kind of boxes here. We also have CO2 emissions from heating our homes, heating buildings, doing transport, so kind of buses, cars, trains, all that kind of stuff, and making stuff. Okay, so these are all things that we need to do. We need to, if we don't heat our homes, and we live in Scotland, we will freeze to death in winter. If we don't make stuff, then our economy will fall. Well, our economy is falling apart anyway, but right, it's bad. Right? So we want to follow this black line, okay, by reducing our emissions. Okay, but if you look at, if we just reduce the blues and the greys, that brings us down, actually following the top of this brown box here. Okay, so that doesn't get to zero. Okay, and to achieve this, we've got to get to not just zero emissions, we have to get to negative emissions. So we're already at the point where just stopping burning fossil fuels is enough. We need to get to net negative emissions. So to do that, we have to fundamentally change kind of the way that our economy works. And for instance, you could change both agriculture, forestry, that kind of stuff, and plant more trees. That's the brown here. So we can maybe make the planet, kind of the biosphere, more effective, and that will do that much. But to actually get down to this line here, we have to do what's inside this orange box and the yellow box. And the orange box is fossil fuel carbon capture and storage. So if we can't reduce our fossil fuel usage, we have to take the CO2 from that and put that in the ground. So taking the CO2 out of the fossil fuel kind of emission flues, that's kind of technically possible. But the carbon capture and storage, the storage part of it, is much less certain. And actually the biggest contribution to future success is this thing at the bottom that says BECCS. That's biomass, energy, carbon capture and storage. So that's growing plants, trees, grasses, all that kind of stuff, and burning them to make energy, and then capturing the CO2 and putting that in the ground. So that will actively take CO2 out of the atmosphere. Now these are quite controversial that we should try these, but there's no way of getting to net zero emissions and below without them. And without Earth scientists, without a fundamental understanding of how the Earth system works, from how you can inject fluids like CO2 into reservoirs, how those fluids can interact with rocks, because CO2 is a highly corrosive acid, it will kind of react with rocks and change their porosity, permeability. It will form new minerals that might actually help trap the CO2. It will also potentially release nasty elements that were stored in rocks into the environment again. So we need to understand those processes. We need to understand what the impact of all of the technological solutions, this, putting more wind farms on kind of peat bogs, is that going to be bad for the peat bogs? Are there ways that we can do that without it kind of destroying the environment? So a fundamental understanding of the Earth's surface, the processes that are happening on it, and the deep Earth as well, where we can actually put these nasty carbon dioxide, is essential for solving this problem. This problem cannot be solved without Earth scientists. So it's really important that people like you, okay, become the people that can do this. Okay? So there you go, that's what Earth science is. So the motivations for doing the subject, people like me, I really want to understand how the Earth works. It's just really a curious, interesting thing to study. It's the thing that we live on. There's also, risks associated with living on an tectonically active planet, so things like volcanoes, earthquakes, floods, weather hazards like increased storminess and sea level rise. Understanding these natural hazards is an important motivation for doing Earth sciences, so that's one reason. And then the third reason used to be, let's go and get some oil and gas, right? But now it's not that, but we still need stuff, right? We need all of the things in the room, we need all the things that the elements that make up your mobile phone, the gadolinium and all that kind of crazy elements you've never heard of. We still need those, and we still need to extract those in a responsible way. And to do that, we really need a fundamental understanding how different parts of the Earth system work. Okay? And also, I guess, this now encompasses this carbon capture and storage thing, which is a strong area of research that Edinburgh is very actively engaged in. Okay, so that's kind of Earth sciences. That's why you want to do it. I mean, it's very hard to give an overview of such a broad subject in such a short time, but hey-ho. But what's it like at Edinburgh? So Edinburgh is kind of where the subject was first kind of founded, and it also happens to be a fantastic place to teach Earth sciences because of the environment around us. Okay, so we have a number of we don't have active volcanoes in Edinburgh. We have a number of different kinds of volcanoes within the city, which we can use in our teaching and understand things like that. We have a huge variety of different kind of geological environments in Scotland that we can use to bring into our teaching, which is really, really cool and important. So yeah, so this is a geological map of Scotland, and the things that you can see on here, that it's all kind of different blocks of different kind of colour. Okay, and these are different kind of geological, I guess we might call them geological terrains, but they're kind of different. They're rocks that were formed under different environments. So we've got the Midland Valley, where Edinburgh and Glasgow are based. So this is a region of the Earth that was formed in the same kind of way that the East African Rift Valley is now. So it's pulling apart, lots of sedimentary basins, lots of volcanoes. So volcanoes all over the Midland Valley here. The southern uplands, this was next to a subduction zone. So this is where sediment is basically being scraped off as two tectonic plates collide. So this is analogous now to basically a region a bit like Barbados. So if you want to go to Barbados, why bother? Go to Moffat instead. It's just the same. Moffat toffee is delicious if you ever stop in Moffat. Anyway. The Grampian Mountains, again, an island arc, but this is kind of more analogous to Japan. So Tokyo or Aviemore, whichever you kind of feel. And then we've got some we've got slices of the deep crust up in the Northern Highlands. We have supervolcanoes on Mull, Ardnamurchan, Arran. There's a huge variety of different kind of geological stuff in Scotland. It's why it's such a fantastic place to study here. We also go to other places as well, because if you want to study active processes, you have to go to where those are actively happening. And here are some stars where we go for no reason. Lots of stars. And we also go to England, because, why not? So just to point out some stuff, so here's one of the volcanoes, Arthur's Seat. There's another volcano up here just behind King's Building site. So where we are here, King's Buildings, about half of the lectures will be here in the first year, another half will be in the central area. It's a 9.5-minute cycle for me, so if you think you can beat that, good luck. Totally stopped all the red lights. So it's quite a compact city. So although we've got different sites, don't worry about getting around. It's fairly straightforward. And as I mentioned earlier, Edinburgh is where the science of Earth sciences kind of was first developed by kind of these guys, James Hutton, Charles Lyell. They were some of the first people that really got to grips with how old the Earth was. Now, that's all well and good, having this history and whatnot, but does it really impact the science today? And you could argue that not really, okay? I mean, most of the stuff these guys came up with is kind of right, but it's not the cutting edge science. So we don't dwell on it too much, but it is quite nice to be able to go to the localities. So this is Siccar Point, which if you've got a geology textbook, this picture will be in it, where they figured out that the Earth must be very, very old. It's quite nice to be able to go with our first, go there, go that, go there. Go there with our first years and show how the scientific ideas were developed. But the reason, oceanography, radioactive dating, all Edinburgh is where it was at. But the reason I show this is actually this guy in the middle, John Playfair. So he, not really a scientist, he's just like a really rich guy. And he was very supportive of the Scottish Enlightenment at the time of Scottish Enlightenment, so around the turn of the 19th century. So he was very interested in science and the development of these new ideas. Didn't come up with many of his own, but these guys did. And they wrote the dullest books. Oh my God, they're so boring, right? Whereas John Playfair was a really good communicator. Okay, so he was really good at taking the ideas of these guys and popularizing them. And this is why I'm showing you this picture, because this is a really important part of our courses, all of the earth science courses, is that we try to instill lots of transferable skills. And communicating your ideas or your findings from your research is really important. And so we have that embedded throughout quite a lot of our courses, but we also have a dedicated course option in the 4th year or 5th year in geoscience outreach, where you can go and kind of develop kind of an idea or a concept from earth sciences and communicate that to some group of the public, taking it to schools, NGOs, or whatever you want to. It's pretty cool. So if you're interested in that, come and talk to me at the stand. Yeah, so we're not just the old dead white guys. We have lots of, fancy pants new staff as well. So Edinburgh's great because we're a really big school. There are a lot of academics here. So this fits into our teaching because it allows us to offer specialist courses in what you want to do towards the end of your course, not just what the academics are available. So we've got people like Steve Prasati, who was on the Infinite Monkey Cage last kind of week, talking about dinosaurs. So if you like dinosaurs, please buy his book. I don't get anything from that, but he's a nice guy. Buy his book. We've got Gabby Hergel, who was one of the lead authors of the IPCC climate report. We've got people like Murray Roberts, who's looking at marine biology and the coral reefs around Scotland, which do exist and are super interesting. A huge range of really world-leading scientists. Now, that's great for research, but all of these people are doing teaching. So we don't have any academics that just do research. If you want to get a job as a lecturer or professor or whatever at Edinburgh, it is impossible to do that if you're not dedicated to teaching. So that's a really good thing about having such a wide group of colleagues, is that they're all doing teaching and research at the cutting edge of what they do. Ooh, don't do that. Right, so a little bit now about our degrees. And again, it's quite hard to cover everything because we have lots of different flavors of degrees. So here's a list of them, but let's just go through them in a more pictorial way. So geoscience is a very broad term. Okay, so you can think of it as maybe there's earth sciences, which are kind of the subjects that like geology and geophysics, maybe more traditionally known as, kind of a little bit of overlap with geography in that, also some ecology. And the point of this Euler diagram here is not to kind of convince you about the details of our courses, but we have lots of degrees, but there is a lot of overlap between them. So there is possibilities of switcherooing between degrees within the first year or whatnot. So as an example, here's a volcano. I am not going to try and pronounce its name, but it's in Iceland. So a geologist might be interested in the processes that led up to the eruption of this volcano. They might be looking at maybe samples of the rock to try and understand the history of the magma chamber. How has it temperature changed through time? How has the crystallization changed? Did any temperature changes lead to the eruption, or was it a process of the removal of gases or the crystallization of a particular phase that triggered the eruption? An environmental geoscience student might be interested in the same volcano, but they might be interested in the products that are being erupted from it. And they might say, well, all of that volcanic ash, how is that going to affect the climate? How is that going to affect the ocean when it lands in it? Okay, you might just be able to make out, here's a plume of the volcanic ash, and then there's this kind of blue splodge in the ocean here. That's phytoplankton that are being fertilized by the ash that's coming out of that volcano. Okay? So understanding that interaction between the volcano and the biosphere is very much an environmental geoscience aspect of this. We might also be interested in the gases that are coming off the volcano and how they're affecting the chemistry of the water, affecting maybe the acidity, which might be dissolving some of the critters that live around the volcano. A GPG student, so geology and physical geography, they might be interested in the same volcano, but from a natural hazards perspective. You know, how does this affect aviation? How does it affect landslide risk or lahars in the region? And geophysicists would be asking all of the same questions. Okay, so they might be interested in the atmospheric effects of this, or they might be interested in maybe using some seismic data to understand the volcano. So they'll just be taking a more physics approach to the same set of questions. So geology, interested in all of these kind of things. So we're interested in how the Earth works from a physical science perspective, but interested in natural hazards, resources, those flavour of things, and also understanding like how the Earth has changed through time. Okay, so looking at these processes, look at that volcano, rather than looking at the current eruption, can we look at the rocks that volcano formed and see how it behaved the last 10 times it erupted over the last maybe 100,000 years? The environmental geoscience degree, again, that's looking a little bit more about the interactions between the environment, okay, the environment being kind of the wet bits that stuff lives, and the solid Earth, looking at the processes that are responsible for sea level change, environmental pollution, those kind of questions. The GPG degree, sorry, everything in Edinburgh has acronyms. So the geology and physical geography degree is very similar to geology, but makes a lot more focus on the Earth's surface processes. So using the physical sciences to understand geomorphology, how the landscape changes through time, and how that might affect the risk from that landscape in terms of landslides, flooding, that kind of thing. Again, looking at things like using remote sensing or geospatial data to better understand kind of our planet. And the geophysics is. Now, it's very hard to cover all the geophysics. We have a variety of flavors of geophysics degrees. One that is focused mostly on meteorology, so climate science, atmospheric chemistry, atmospheric physics. One that focuses on the interactions of geophysics and geology, and then one which is kind of like just geophysics, which allows you to take kind of a much broader approach and take maybe a bit of kind of climate science stuff and a bit of kind of earth stuff as well. So I guess geophysics is really for those that want to really use physics and maths to understand problems about how the Earth works. And these are like questions and words that are related to geophysics. There you go. Okay, so the structure of our degrees. So for all degrees, there's this period which we call the pre-honours. So in most Scottish universities, that lasts for 2 years, where you'll take a range of core subjects for your degree and some outside courses as well. Now, that doesn't count towards your overall degree classification. That's kind of just to prepare you for the honours years. There's quite a lot of flexibility to switch between programs. Now, that does depend on the option courses you have taken. There's a little bit less flexibility with the geophysics degrees because we have to make sure that you've done lots of core courses in physics and maths. For all of our degrees except the geology and, the geophysics and geology, there's this option to do fast track where we condense all of the core courses that you would do in the first and second year into 1 year. So you don't skip the first year, you just don't do lots of option courses. We make you do all of the courses in the 1 year. And you just have to pass that. Okay? So there's kind of like a barrier here. You've got to pass credits from pre-honours to get into the third year. So once you get into the third year, stuff starts counting towards your overall degree classification. And in the third year, we're really trying to prepare you for the fourth year and your honours dissertation. So there's a lot less choice. So some degrees of the geology and physical geography has a little bit more choice, but most degrees narrow down the choice in the third year to make sure that you're prepared for the fourth year. So we do a lot more specialised courses in the third year that are unique to each degree programme. And then in the senior honour years, you do a project. So in the geology degree programme, that will be kind of making a geological map of an area, and we'll see an example of that on the tour we'll do in a bit. Whereas for the other degrees, that will be more project-based, although those projects can also involve a lot of fieldwork if that's something you're interested in. For most of the degrees, there's also this option of doing this integrated masters. If you're interested in doing research, this is a really good opportunity to effectively do the first year of a PhD and try it out, see if you like doing research. So it involves a lot more independent work, much larger research dissertation, and master's level courses. So just briefly, these are the kind of the structure and courses for the geology, the environmental geoscience, and the geology and physical geography degrees. So the first years are the same. If you've not done maths higher or maths A-level, we'll ask that you do at least some maths. We might suggest that depending on which degree you're doing, you might do a bit more maths as well. Just to make sure that you're prepared for the science of the science degree. But you'll all do courses which are kind of introducing the Earth system. How does plate tectonics work? How do earthquakes work? Where do we get volcanoes? That kind of thing. We have a course called Introduction to the Geological Record, which introduces the skills of making observations of rocks, minerals, and has a field trip associated with that. And then Evolution of the Living Earth is a course which brings kind of the history of how life developed on Earth and how that changed the planet's chemistry and physics through time. So it has a little bit of chemistry, a little bit of physics, and a little bit of paleontology. So you get Steve the Dino guy in that one. In the second year, you start to specialise into the degree that you've chosen. So at the end of the first year, it's very easy to switch between these different flavours of earth science degrees. So everyone does a course on geomaterials, which is a subject which is about the properties of the stuff that the Earth is made of. This used to be called mineralogy. I don't know why we didn't call the course mineralogy, but it is. But then the geologists start to specialise. They do a bit of geophysics, a course on how kind of the forces and results of plate tectonics affect how rocks are formed and which rocks are formed where. So that's global tectonics and the rock cycle. The environmental geoscience students do oceanography and a bit of environmental geochemistry. It's looking at pollution and nutrients and how they move around the Earth's surface. And the geography students do a bit of geomorphology. Now you'll notice that there are a bunch of options here. So if you were doing environmental geoscience and you weren't sure you might want to do geology, you could put some of these kind of courses as your options, keeping the switcheroo option open up until the second year, end of the second year. Geophysics is a little bit more constrained. So we have basically a first year which is the same as a physics degree, except that the two options are taken up by these Introduction to the Earth System courses. And then again, in the second year, you start to specialise into the flavour of geophysics which you're wanting to do. So if you want to take a more climate sciences, meteorology kind of route, you take courses in climate science and meteorology. If you want to take a more geological route, you take some geology options. And if you don't want to do that, you can do just geophysics and then maybe take some of these as your option courses as well. So again, you'll also be doing some more maths and physics. Okay, so looking at the fourth year, these are the third year, junior honours years. We're basically making you do a whole bunch of courses, giving you a few options. So there's two options in geology. There's quite a few options in the geology and physical geography. But the environmental geoscience and the geophysics degrees are really reducing down your options to make sure that you're prepared for the stuff that comes in the final years. I won't read all of those out, but we're still keeping the scope quite broad, although there are no options. The final year, you'll be doing this honours dissertation, so that will be a third of your final year, so it's quite a substantial amount of work. But we still have some talk courses which kind of bring together all of the stuff that you've done throughout your degree, and then some options. So how are we doing on, oh, we're already at the end of when I should have finished, but anyway. So, yeah. I guess the thing that makes Edinburgh a little bit different is that we really try and make use of the world around us to do our teaching. So we try and incorporate field trips, not just into the field courses where we go away for a week or so and do some observations and some experiments in the field, but we also try and incorporate it throughout the taught courses. So for instance, we have a course on sedimentology and paleontology that rather than do the practicals in a laboratory, we go out into the field and do them kind of on day trips. And yes, I've already mentioned that Scotland is like a fantastic place to do that. So having a university located close to all of these fantastic places to do a whole range of different kinds of earth science activities is pretty awesome. We also go to places that are not in Scotland, so Cyprus, Jamaica. The Iceland trip for the 5th years didn't run this year. Students went to Tenerife instead to look at an active volcano there. Cyprus and England. Got to have England. Right. Study abroad. There is an option for most of our degree programs, except the environmental geoscience degree, to take the 3rd year abroad. And we have a number of exchanges set up with other universities where we've kind of made sure that the 3rd year matches well enough that you can kind of come back and do the 4th year without any problems. But that being said, you don't have to go away to get an international experience at Edinburgh, because the world comes to Edinburgh. Okay? We have lots of students from overseas on our courses. We also have lots of visiting students. So you'll get an international experience just by being here, which is quite nice. I guess I'll just mention quickly that the teaching is not just lectures like this. We do a variety of activities in the lab, doing practicals and whatnot. But we, as I've already mentioned, do fieldwork as well. We try and also mix up our assessments. So it's not just kind of writing lab reports over and over and over again. We try and make our assessments varied so it makes it kind of, I guess, more bearable for students, but also to bring in these transferable skills. So, for example, one of the courses that I'm involved in is a field course to Oban in the Highlands, where we go out on a boat and we do some chemistry sampling of some of the lochs up there. And students write a scientific report about that, but also one of the assessments is to make basically a science outreach leaflet for a specific target group that the students decide. So it might be targeting like something about how the chemistry of the loch affects fish and trying to target that message to 9-year-old school kids or to Japanese tourists. I did make the mistake of saying that they could do it in any language, and one year I had to read one that was in Korean, which was challenging. But Google Translate came to the rescue. Anyway, so we try and mix up the assessment as much as we can. So it's not just kind of like tests, lab reports, essays. There's a huge variety of stuff we do. Yeah, I guess I mentioned earlier that you have to be dedicated to do your teaching to get a job here, but we also have this institute within the University for Academic Development, which is really quite useful to have. So we're constantly, basically teaching staff are using this to develop their skills through the course of their careers. So it's really great to have the support to help us do that. But support for students exists as well. So when you come, you'll have a personal tutor that will be able to kind of advise you on courses to take and whatnot. But that's not your only source of information. We have a very active student support system to help students help each other learn, which is by far the best way of learning, called GeoPals. So if you have a chance, talk to some of the students that we have to kind of show you around. Talk to them about that. There's also a dedicated system of pastoral support that's separate from the personal tutors. So we make this very conscious effort to separate the academic help from the pastoral support. Okay? So we have dedicated student support coordinators for that, which kind of liaise with the Students' Union and the chaplaincy and the advice place, which are where students can get all kinds of help. So when you're here, you're very much not on your own in terms of your kind of like life and also your kind of like learning stuff. We also have a whole bunch of kind of like, technical support where students get help with IT issues and stuff like that. But also if there's like skills that you want to develop in kind of computing, or how to write better essays, or how to make a better poster, we have lots of kind of help for that within the school and also out with. Just quickly, because we're running out of time, when you leave, you want to get a job, because, those bills don't pay themselves. Now, it used to be the case that Earth Sciences was just, let's go and, off you go, BP will take you, you'll earn loads of money. Some students take that route, they go work for oil and gas or mining companies still. But by far, the biggest area that our students start to work in now is in kind of the environmental sector. So working for kind of as a hydrogeologist, a contaminated land manager, working for NGOs or environment agency type organizations to do that kind of thing. I think roughly about half of our students go on to some kind of further research as a dedicated master's or a PhD. And of course, you will have a physical sciences degree. So all of the careers open to people who are quantitative, who are able to kind of write concisely, clearly, kind of communicate their ideas, are available to you. So all of these kind of like, I wouldn't say generic jobs, but they're non-specific to the degree. Our graduates are still highly sought after in those. We have a dedicated careers service. So there's the university career service, but within that there's a person that just deals with the geoscience students that can help with getting internships and building your CV in such a way to make you kind of more employable. So it used to be, when I was at university, if you went to the career service, that was a sign of weakness. Right? That's really not the case anymore. They are a really kind of useful bunch of people that do all kinds of useful things for our students. So we've got them. Okay, so I think that's the end of this. Just to point out that these are our kind of like general stuff that we'll be doing in terms of offers. There are the possibility of having reduced kind of slightly lower offers if you're from a disadvantaged background or your school is on a list. There are also some opportunities for flexibility on our offers. So if we give you an offer of 3 A's or 4 A's or whatever, and you just miss that, it is possible to, I'm totally on it, great. You always get thrown out. I was talk so much. Anyway, so on clearing, it is worth kind of just going, hey, I got AAB. How about it? And we're like, yeah, okay, maybe. Obviously, we can't like give firm guarantees of that kind of stuff, but it is worth considering that we're not always kind of, no, you're out, because maybe not. Okay, so really, there's more. Okay, yeah, Earth Science, yeah, okay. I did write this presentation. Yeah, so Earth Sciences, I can't imagine why anyone would not want to do Earth Sciences. The Earth is so fascinating. Edinburgh is also a pretty good place to do it. Right, so I won't take any questions now because I'm being thrown out of here. So if you do have questions, you can use this email address and it will get to me. Or we're going to go on a little bit of a tour and go up and have a look at one of the teaching labs. So you can ask me then, or come back to the Sanderson building sometime later in the day, and I'll be there. Okay, let's go. Yeah. Woo! Yeah. Okay, yeah, so we've got Emma and Hannah will guide you up to the lab.